Hi everyone, today we're going to learn about electron configuration. So there's two ways of writing the electron configuration. The first way is by using the periodic table. The second way is by using this method, which is we're going to write the levels that we have, or the quantum number, the energy levels, S2S2P, 3S3P, 4D, 4F, 5S, 5P, 5D, 5F, and then 6 S, 7P, 8S. So let's say we have nitrogen, for example. It's an easy one to write the electron configuration for. So it has 7 electrons, so 7 nitrogen. I mean like 7 electrons in nitrogen. So we know that S can hold 2 electrons. P can hold 6 electrons. F can hold 14 electrons. And I hope you saw the trend that from going from S to P to D to F to a higher sublevel, as we're going from a higher sublevel, because S is higher than P and P is higher than F. So as we go into a higher sublevel, we're increasing by 4 electrons. And you can see that from 2 to 6 and 6 to 10 and 10 to 14. So let's erase this. If we want to write the electron configuration for nitrogen, we will start by 1s, and we know that S can hold 2 electrons, so we're going to write 1s2. S can't hold more than 2 electrons, so I can't write something more than 2, like 1s3 or 1s5. That's incorrect. S just can hold 2 or less, so I can write 1s1, but I can't write more than 2. And then 5 electrons, because S holds 2 electrons. And we have 7 electrons, so 2s2, we're going diagonal, and then 2p, have 4, we're left with 3, so 2p. This is the electron configuration. And we have another type of electron configuration called by noble gas electron configuration. Is by writing one of the noble gases. If you're going to see the periodic table, it's really bad drawing. This is good. Okay. So we have He, helium, and so on. So the noble gas electron configuration is using one of the noble gases. Let's say for this example, we know helium holds 2, so we'd write have 2, so we're left with 2s2, 2p3. Okay, why did I did that? Because I want my electron configuration to be smaller, and you would see that when we would write for something like iron or gold, we have a big number of electrons, and we don't want our electron configuration to be really long. We would use noble gases. But for this example, it really doesn't, doesn't get any shorter because it's literally the same. We just got rid of 2 electrons. Because helium holds 2 electrons, I will get rid of 2 electrons. So as we are, because we have helium which holds 2 electrons, we would write the remaining electrons, which is because we have for nitrogen 7 electrons, and helium has 2 electrons, so let's subtract 2, and then we would write the remaining electrons. So let's click for another example. So let's try another example, which is, let's say we have potassium, which is 19. So 19K, and then we need to write the electron configuration of it. So we need to have this 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, and 4. Okay, I don't have space. That's fine. That's enough. So because we want 2 electrons, we will go diagonal, so it will be 1s2, and then 2s2, 2p6. So until now we have 10 electrons, we are left with 9. So 3s2, and then to 3p, and then 4s1. So now we have 19 electrons. We can count 2 plus 2, 4, 4 plus 6 is 10, 10 plus 2 is 12, 12 plus 6 is 18, and 18 plus 1 is 19. So we can in here write the noble gas. So this is the noble gases, which we start with helium, and then argon. Yes, that's enough. So argon has an 18 electrons, and that's good because I want less electrons or the exact same number of electrons that this element has. So I can write Ar with those, with those squared brackets, and then 4s1. So Ar has 18, and 18 plus 1 will give us 19, which is potassium. So the second way of finding the electron configuration is by using. So this block is S block, this block is the D block, and this is the P, this is the D block, and this is the F block. And those we know as the period 1, period 2, 3, 4, 5, 6, and 7. So let's say they want us to find the electron configuration for oxygen, which is 8. So we would do 1s, so 1s2, because this is even s block, and then 2, which is n, which is the energy level, 2s2 because it's 1, 2, and then 2p, 1, 2, 3, 4, 4 oxygen. And we can do it in the method that I just showed you, which is 1s, 2s, 2p equals 2, so 2 would go, we just wrote that, and then 2s2, s holds 2, so that's 4, and then we are left with another 4, which is 2p would be 4, and ones are 4 plus 2, which is 6, because we would count because 2 is the highest energy level, and we'd count the electrons that is in that high energy level. 2 is the core electron, which is the electron that's being left. Let's try another example. By sodium, which is 11, has 11 electrons, which is somewhere here. So 1s2, because this is 1, 2, then 2s2, 1, 2, 2p6, 1, 2, 3, 4, 5, 6, and then s1 because it's 3, and then s the block, and then one step through that s block. The valence electron would be 3 s1, which is 1 valence electrons, and those would be the core electrons. Electron configuration of sulfur, which has 16 numbers of electrons. And let's use this method, 1s. P and 4f. So we know S has 16, so we would always start with 1s, which holds 2, so 16 minus 2, which would give us 4 or 14, and then 2s2, which we will have 12, and then 2p6, which would get rid of 6, which would be another 3s2, which would be 3p4. So this is the electron configuration of sulfur. And let's say um, they wanted to not balance electrons, so it will be 3 and 3. Balance electrons that they hold, which is 2 and 4, so 2 plus 4 would give us 6, and the core electrons will be those. Electron configuration. We know that the noble gases are helium. Yes, we would. Yeah. So neon has 10 electrons, argon has 18, and helium has 2. And because this has 16, we can't get more than 16 electrons, so argon won't be the one to be neon. So neon has 10, so we're left with 6, and the 6 will be from those. So 3s2, 3p4. This is the noble gas electron configuration. This example. Let's say we have sulfur with which is an ion sulfur. Let's say to the it's gain 2 electrons. So united, so it already has 16 plus 2, which would give us 18. So we would use 1s, 2s, 2p. You can use the periodic table method by just using this method right now. So we have 18. So we will always start with 1s2, 1s2, and then 2s2, 2p6. So until now we have 10, so we're up to date. 3s2, we're left with 6, and this is the electron configuration for minus 2. Let's say s plus 2. When we get to it, so that's how you write this. So the sulfur already has 16 electrons, and we would want 2 from the 16 electrons, which would give us 14. So it will be 1s2, 2s2, 2p6. We're left with 4 electrons, which would be 2p6, s2, and then 3, 2. And the core electrons will be those, and valence electrons would be this, which is 4 valence electrons. And let's say they want us to write it as a noble gas electron configuration. So He and EAR. We know He holds 2, and E holds 10, and AR holds 18. Yes, 18. And we have in here 14, so we'll go with Ne. Then we're left with 4. So it will be 3s2, 3p2. That's all. So we have exceptions to the methods that I've shown you, and those exceptions being discovered experimentally. So for copper and silver and gold and so on, for the method that I've shown you, it won't work. Reason is because 3D is higher energy than 4s, and it's the same as we're going down. The D subshell has higher energy than PS subshell. And so if you would have like 3 and 4, always say that, because n equals higher number, that means it has higher energy. Well, that's incorrect. I don't think you need to know that yet, but for this, so to understand the exceptions, you need to know that D sublevels are higher than the S ones. So that's the reason when we would always like the D sublevels to be either half full or fully filled. So it's either 10 or 5. And this is what's happening in here. Our energy doesn't need that much of electron, so I will give 1 electron to the 3D because it has higher energy and it's due to be filled or half filled. And it's the same in here. In here what's going on is literally the same, but we have like it's the same. Well, here it's even the same because we would get rid of the both electrons, so it will be filled in here, but we'll get rid of the 5s2. And in here I would make it half fill because I don't have enough electrons to make it fully filled. So it will be this one. And then it's the same, I don't have enough electrons. So those exceptions, I would like you to know them because it's my IPO in the test. But the most common I have seen is those three. But just know them and know that the D sublevel are higher in energy in S sublevel, but it's not that much of a higher energy, it's a bit of higher. That's why we see those exceptions. And I hope you gained something new.